Okay, welcome and welcome back. So today we're talking about balancing chemical reactions or the art of stoichiometry. The idea that if we put something in, if we take a Lego structure built with 25 Legos and we break it apart and rearrange it into some new structure with those same 25 Legos, what we know is that the number of blocks is the same, the number of colored blocks will remain the same, the weight before and after will remain the same. It's a rearrangement of the existing starting material into something new, and that exchange has to always be conserved. Mass and matter must always be conserved. This was an idea that was brought not exclusively, but really coined and cemented, solidified around by Antoine Lavoisier, shown here, with DuPont, the chemist, the French-American chemist, and starter patriarch of the DuPont chemical empire, pontificating about his phlogiston experiment, in which he disproved the existence of a substance called calx, which was thought to, or phlogiston, excuse me, that was used or consumed during a chemical reaction, a combustion process, but not understanding how when something burns, it gains weight, it gains a calx, later known as an oxide, a metal oxide, if it was losing its phlogiston. And so this is um, what Antoine Lavoisier's studies, along with other chemists, came to realize, which was that phlogiston is not something that was lost, and calx was something that was gained, oxygen that was gained going from mercury and oxygen to mercury oxide. But furthermore, what this understanding that phlogiston doesn't exist, oxygen was the thing that was adding the weight to the mercury oxide, the metal oxide. He realized that however much mercury and oxygen we started with in the reactant side of the chemical reactants reaction, we need to have the same amount of products, both in mass, in actuality, but in the balanced chemical reaction and the representation of how many elements, how many Lego building blocks exist. So in a chemical reaction, both in the products and the reactants, we have two different types of numbers. The stoichiometric, the balancing coefficient that tells us how many of each molecule are there, be it two mercuries or two oxides that are there to make sure that we have a consistent number, two mercuries here and two mercuries there. We also have the subscript of how many of each element are existing per molecule. There are two oxygens within this molecule, and therefore there are two mercury, two oxide molecules, so that we have two oxygens on the product side. But the goal is always to make sure that if we have two mercuries reacting, we have 2 times 1 mercury coming out. If we have 2 oxygens reacting, we have 2 times 1 oxygens coming out. This arrow indicates the yield, the direction of the yield, where we're starting and where we're going in the chemical reaction as the reaction is set up. Many, and if not most, reactions are reversible, but that's for your chemistry class. And then finally, we can note the phases of matter in our chemical reaction and how they change from the products of a liquid and a gas to the reactants as a solid. So let's do a couple examples of chemical reactions. In this primer, we're not going to discuss how to determine what the reactants are. We're going to assume that you know what the chemical reaction is, where we're starting and where we're ending. Our only goal today is to be able to balance that chemical reaction so that matter is conserved. Whatever we start with, we end with. Whatever Legos we start in our first structure, when we rearrange into something new without adding any Legos or taking any Legos away, Sorry, I got young kids. Then the mass and the number of Legos and the color and size of Legos has to be conserved. Legos don't disappear or come out of nowhere. See this in action. So let's write the balanced equation for the reaction between solid cobalt-3 oxide. So we have cobalt, which is 3 plus, and oxygen. So we're going to need 2 cobalts, 3 plus, and 3 oxygens. Go look at how we balance the charges when we make molecules in the boot camp module for that, if you need help there. But we know that that's solid plus solid carbon, which elementally is just C. That produces solid cobalt and carbon dioxide gas. 2 gas. So the first step that we're going to do is just take the nomenclature and write the unbalanced chemical reaction, which we've done, listing the states of matter as they're told to us or as we know. Then we're going to balance the atoms in the more complex molecule. So start with the thing that has more different elements, a larger number of different elements, the more complex molecule. It's easier to settle that score first and then go to the independent elements and try to balance those. So if we look here, there are 2 cobalts on the product side. So we need to have 2 cobalts on the reactant side. So we'll put a balancing 2 there. We are only going to put the subscripts in for the nomenclature, what that molecule is expected to have of each element. Then when we want to balance the chemical reaction, we're going to use the balancing stoichiometric coefficients to make sure there's the same number on both sides. Here we have 3 oxygens, and so we're going to need 3 oxygens over here. And so to get 3 oxygens, there's a couple approaches I can have, but I have O2 and I want 3 of them. And so one thing that I can do is just say 3 halves. I can use fractions, and 3 halves of a molecule doesn't make sense now, but it does get me balanced the way that I want to. And then we can get rid of the fractions at the end. So if I multiply O2 by 3, I have 6 divided by 2 is 3 oxygens, 3 oxygens. And now I have 3 halves of a carbon. I don't know what that means, but I can put a 3 halves of a carbon over here. And now I technically have a balanced chemical reaction. Balancing the atoms that occur in free elements last, that would be the carbon, 3 halves carbon. So that's a way to do it. Of course, 3 halves of a carbon doesn't make sense. And so to get rid of the coefficients, we're going to multiply by the least common denominator to get rid of the coefficients, which would be 2 times 2. And as a result, this 2 becomes a 4, and these 3 halves become a 3. We'll put a 2 here. That 1 becomes a 2. The 3 halves become 3s, and this 2 becomes a 4. We can erase this times 2. And so now we can check. We have 2 times 2, 4 cobalts, 4 cobalts. 2 times 3, 6 oxygens. 3 times 2, 6 oxygens. 3 carbons and 3 carbons. And there is no number, no whole number that we can divide all these coefficients by to reduce them any further. This is the least common denominators for this to balance. And so this is a balanced chemical reaction for the reduction of cobalt. Let's try another one. The combustion of hydrocarbons is always kind of a classic balancing act. So let's try it. We have liquid octane gas, so used in cars, car engines, along with some other hydrocarbons. In its liquid form, plus we're going to combust it. So that's a reaction with O2 gas. Oxygen in its atomic, or its natural form, excuse me, is diatomic, O2, always. And then carbon dioxide and water, CO2, gas plus H2O. It's going to come out as a gas from the engine. So let's go to the more complex structure. First, C8H18, octane. There's 8 carbons, which means we're going to need 8 carbons over here. And there are 18 hydrogens. We get 2 hydrogens in each dihydrogen monoxide, aka water. So we'll need 9 waters. 9 times 2 is 18, 18 hydrogens. So that's all good. And then we're going to have 16 plus 9, so 25 oxygens, 16 here, 9 there is 25. We have O2, so 2 oxygens over here, and the oxygens are coming in as pairs, which is a little bit challenging with an odd number of 25. But again, let's not fear fractions to get what we want. So we want 25 halves. 25 divided by 2 times O2. 25 times 2 is 50 divided by 2 is 25 oxygens. So it's like if we cut all the O2s in half and then took 25 of those halves, we'd have 25 oxygens. So the equation now is balanced: 8 carbons, 18 hydrogens, and 25 oxygens. But 25 half oxygen molecules doesn't make any sense. So we can multiply everything by 2 so that we get our least common denominator of whole numbers. So that 9 becomes an 18. That 8 becomes a 16. The octane will get a 2, and then the 25 halves times 2, get rid of that, becomes 25. There is 16 carbons, 16 carbons. There's 2 times 18, 36 hydrogens, 18 times 2, 36 hydrogens. And then there is 16 times 2, 32 plus 18 is 50 oxygens, 25, 2 is 15 oxygens. And there's no number that we can divide out by all of these coefficients to reduce them any further into a whole number. So this is the least common denominator. And this is the balanced chemical reaction for the combustion of octane. Let's try one more example together, and then I'll turn you over to the practice assignment, and you can come back and check your answers with me when you're finished. But let's write the balanced chemical reaction between aqueous potassium iodide and aqueous lead-2 nitrate. So it's a precipitation, a double displacement reaction to yield a solid, a precipitate lead-2 iodide, and an aqueous potassium nitrate spectator ion. So again, go to your chemistry class to learn about how to explore these chemical reactions. Come here to balance them. So potassium iodide, Ki. Go to the nomenclature boot camp modules if you need help with nomenclature and being able to pull from the words the chemical reaction. But plus lead-2 nitrate, so Pb 2 plus NO3 2 aqueous to form lead-2 iodide solid plus potassium nitrate, K. So there's our unbalanced equation. I'm going to look at the more complex, if such a thing exists, lead-2 nitrate, and I want to balance that. But before I go any further, I want to make sure that we understand one idea of aqueous chemistry, these kind of ionic solutions. This nitrate, NO3, is one molecule which has gained an electron. And that nitrogen and 3 oxygens with its added electron are going to stay together as a single unit unless we do a different kind of chemistry To oxidize or reduce, to change the number of electrons, change that electronic structure, and we can really change the molecule. But when this dissociates and rearranges, it's going to be three structures, a lead 2 plus and two nitrates. And we can count these nitrates as their own individual unit, and we don't have to count one nitrogen and three oxygens individually. So with that being said, if we have two nitrates over here, then we're going to need two nitrates, because when this potassium nitrate comes apart, dissociates, it's 1K plus and one NO3 minus. And so we're going to need two nitrates over here so that we have the same number of nitrates on the products and reactants side. But that coefficient means that we've added two potassiums to make that true. So we go over to the product side, and we're going to need a coefficient here of 2 to have two potassiums on the reactant side. That added 2 coefficient means that we have two iodides on the reactant side. So let's double check that we have two iodides on the product side. And sure enough, we do. PbI2, lead 2 iodide, which is our solid precipitate, has two iodides and balances the chemical reaction. So while you can balance a double displacement, a precipitation reaction, or an acid-base reaction by the element, it is more efficient and it makes more sense if you know that the ions will stay together and just rearrange to balance the ions as a whole, and it speeds up the process a great deal. So I recommend going now to the practice assignment, seeing how you do with balancing chemical reactions, checking your answers with me, and then getting more help if needed. All right, thank you for your attention.